Yeah, Amina pointed out that the title I submitted is not the title I wrote on the board, so I apologize. I want to thank the organizers for inviting me. I haven't had the chance to spend a lot of time with Minyong yet, but I have had a chance of hanging out with many of his students. So I want to thank him for creating such a wonderful community. They're all really fun to talk math with. So thank you for building a nice community around you. I was also lucky to get a very special birthday treat this year. I heard Minyong speak at our seminar, and it was like really inspiring to see someone bring together, two totally different. My undergrad degree was in physics. I didn't think I was going to hear physics talks again, but like the geometry and physics seminar, it was all very cool. So yeah, thank you. And I think I already apologized to Jan. I could have talked about Shavuti-Kim theory, but then I thought I'd talk about something slightly different. Hopefully it still has many of Minyong's favorite things. There'll be curves, Jacobians. It's about a curve embedded in its Jacobian. There'll be some Galois cohomology, and secretly also a fundamental group behind the scenes. I don't know if I'll bring it up, but like this, certainly some of it is inspired by what goes on in Shavuti-Kim theory. Yeah, so let me get started. So this whole story, I'm hoping it'll be a gentle introduction to this thing called the Charissa cycle that showed up in Dick's talk. There have been many exciting new results about Charissa cycles in the last few years. So I'm hoping to give a very nice leisurely introduction to what this object is and how people have been thinking about it. And at the end, present some results joined with that started at a workshop at PCMI, again, a nice community building thing that happened a few years ago. This joined with Jordan Ellenberg, Adam Logan. Akshay Venkatesh was also very much involved in the conversations. So yeah, we credit all of them. And hopefully the paper, I was scrambling to get the paper up on the archive before the talk and too many LaTeX errors. So hopefully it'll appear by sometime next week, right? So this talk, the main player is a curve inside its Jacobian. So let's give ourselves a nice genus G curve. Over some field K. I stay agnostic about what kind of field I'm working over. So we're going to start with a nice curve over a field together with a point. This curve, K point. So what can you do with the curve and a point? You can use this to embed the curve, nice dimension one object inside this higher dimensional group, the Jacobian of the curve. So this is a nice G-dimensional projective group variety. We like curves very much, but we like groups even more than we like curves. So we stick our curve inside this group. And just to make the connection with like what's going to happen later on, where we like step up the dimension, let me just briefly say, remind everyone like how we build the Jacobian. The Jacobian's canonically built out of points on the curve, right? So this is the quotient of, this punctuality, of course, but you start with all degree 0 divisors on the curve. It's a pretty large group, but you impose an equivalence relation between points on curves. You say certain points, collections of points can be deformed to certain other points if they appear as fibers along a map to P1. So like degree 0 divisors, mod principal divisors, and I will write this in a funny way to make the parallel with what's about to come better. So I think of degree 0 divisors as homologically trivial zero cycles, so zero dimensional subvarieties inside X. So the degree map on the free abelian group of points, you just think of extending a point to its homology class modulo so-called rationally trivial divisors. We're going to do all of the higher dimensions. And this map is just sends the class of a point to a class in this, or whatever, this quotient of this free abelian group. We look at, make this degree 0, we subtract off our base point P, right? So this, one of the miracles is that this group that we build out of points of the curve is once again the points on another algebraic variety, namely the Jacobian, right? And like many of, okay, a little bit, I told you it's going to be a leisurely historical introduction, let me also point out one of the main questions. Once we first we learned that there is this very nice algebraic variety, although higher dimensional, a nice algebraic variety we build out of the question. We can ask, okay, how many points does it have? Right. So this question drove much of last like 2 centuries in mathematics. And how do we understand points on this variety that has this kind of functorial construction, right? So how do we get our hands on points on the Jacobian? And like, how large is this group? J of k for any k should be a group. How do we understand how large the group is? So the way we understand groups is mapping them into other groups, right? So this question, of course, the answer depends on what field you're over. And over the complex numbers, right, you can map points in J of C to this nice torus. This is result of Apple and Jacobi, right? You have the nice integration map that maps points on J of C onto this torus. More canonically, it's you take a differential form on the curve and you integrate against that differential form, right? And it's only well defined up to period. So it's the picture, like drawing pictures. You choose your, if you want to map the class of x minus p, choose your favorite path connecting p to x. So you're writing these as the endpoints of some chain, boundary of some chain. And then the map just sends x minus p to the integral along this path to the functional that sends omega to the integral of omega along this path. Right? And this, okay, of course, depends on the choice of path, but you get something well defined. And one of the miracles is that this map's actually an isomorphism. So you know exactly how large this group is. And this integration map tells us everything about this group. Right? So over a large field, this group is pretty large. At least we know what it is. And over a number field, over small fields like number fields, one of the main theorems is that the model wave theorem, theorem that tells us that this group starts with everything over a number field. And we look at the k points, you actually end up with a pretty small group. You have something finitely generated. And again, the main tool here is like understanding points on a random algebraic variety set. We try to map points on the Jacobian into easier groups. And okay, here's the standard group. The key tool for understanding rational points on the Jacobian is to map it inside the standard group, right? So it's called a homology group. Oops, no, I should not do that. It's wrong. What was I writing? So the key tool for proving finite generation was mapping points or like degree zero devices on the curve inside the standard group. So today, okay, this is something that's classical, well known. What am I going to tell you about? The main topic of today is to study. We started with a nice curve, a one-dimensional object, and we built this G-dimensional group variety. Now, my starting point is going to be this G-dimensional group variety, and I'm going to study one-dimensional subvarieties inside it. And so today, study one-dimensional subvarieties. Before we will try and ask like analogous questions. What we first did. So I'm going to, instead of degree zero divisors on curves, I'm going to be looking at, which is like the free abelian group on points on the curve. I'm instead going to start with the free abelian group. Change free abelian group on one-dimensional subvarieties. Yay. let's say divided over K. And okay, let me give you an example. Find a way. Or maybe like a chance for everyone to wake up Thursday afternoon, end of a very nice, very long, long week of talks. Do we know any one-dimensional subvarieties inside the Jacobian? Want to make an element in here? Yeah, we have X itself, right? We can look at the image of the curve. We have X inside J. I claim that actually, you know, two subvarieties, like you can embed X by sending X to X minus your base point, but you actually also know a second copy of the curve. J is a group, right? So you can hit every point on this curve by the -1 involution. Said differently, you have a second embedding of the curve inside the Jacobian, sending X to P minus X. And I call this mirror image X minus. And the main definition, the main player of today's talk, the Charissa cycle, is the difference of these two inside this POB group. The Charissa cycle, CXP, by definition. Inside this Abelian group, I'm allowed to take formal differences, so I will take the difference of the curve, images of the curve under these two embeddings. Right? So, I mean, yeah. Dick says he's like.
Sorry, I have a stupid question. So if X is not a rational point, so X minus B might not, so it's not have degree 0, right?
Yeah, but I'm starting with P and X of K.
You mean X. If X is not rational, then X minus P is not a degree 0 divisor, right?
I'm just saying what this is at the level of points, like and I'm looking at the entire image of the curve inside J. Yeah, you can talk about close points or like, you know.
If you took a higher degree close point, you would subtract that degree times P.
That many, yeah. That multiple of P. So, but what I'm doing here is taking the entire curve inside X. That's like one object, one element of this free abelian group, and I can formally subtract off this other copy of the curve. Right? So there's a well-defined object in this free abelian group, and that's the main theory of today. This is the Charissa cycle that showed up in Dick's talk. And he might not like it, but one way to remember, if you forget everything else in this talk and you want to remember what the Charissa cycle is, you can sing to yourself X minus, put the minus signs in the right places. So I'm going to do this. Sorry, I apologize for the rest of the talk now if I forget the base point. Okay. Okay, so this is an element in this free abelian group. You should think of this as divisors on the curve, but like we have a whole filtration on like divisors on the curve. So and there's an analog in high dimension. So here's, should I put this in here? Maybe I should.
Does this depend on the fixed point P?
Yeah. Right now, yes. Yes. So that's actually bad. I put that in quotation marks, but yes, it certainly the cycle just does depend on what P should be. But if you start deforming the cycle, then like,
That's the thing that's bad about the notation.
yeah, it's forgetting the base point. Oh no, I made a point of it.
Just put a sub P in there, X sub P minus X sub P.
But it's not so nice to say. Okay, yeah, sure.
Make people happy.
I have a bad feeling that now people are going to pay very close attention to the base point all through the talk, and I'm going to trip up many times. All right, so we built this big, humongous free abelian group on all one-dimensional subvarieties inside J, but that's a pretty large group, and we want to cut it down, work with something smaller. So just like with divisors, we don't work with all divisors. We look at something slightly smaller. We look at the degree 0 divisors, right? So this is like degree 0 divisors. And what is this? Just like you have the degree map in general in higher dimensions, the homologically trivial cycles are the kernel of the cycle class map. From, if you're over C, at least just think about sending a subvariety to its class in homology, right? So you're a nice enough variety, it's class in homology, right? So yeah, G minus one. I might later on want to work with things like finite fields. So I picked a fancy cohomology theory, but like over the complex numbers, you can just think about sending a variety, forgetting everything except its homology class, right? And this is the group where like subgroup where homology doesn't tell you anything. These are all the cycles that go to zero under homology. So this is like the analog of degree zero divisors. And you also have the analog of principal divisors. So you have a subgroup of rationally trivial zero cycles. So this is still a pretty large group, and we want some way of deforming cycles to each other, some natural way of talking about which cycles are the same as some other cycles. And one way to do it is to look at cycles that deform to each other along a P1, right? So by which, I mean, and look at divisors of functions like we do for principal divisors, but now your function is defined on some two-dimensional subvariety inside J. Take your favorite two-dimensional subvariety, pick your favorite function. So this gives you a vibration, and then you say, okay, I'm going to identify the fiber above zero and fiber above infinity. Okay, so this is like the principal divisors. You can see I left a lot of room here because in higher dimensions, you have room to squeeze in potentially new subgroup. It's not at all clear that this is something new, but you have the subgroup of algebraically trivial algebraically trivial cycles where the main difference is you change this. Instead of looking at curves that deform to each other along a P1, you replace this by C and arbitrary algebraic curve. Okay. So we have this whole sequence of subgroups, and so the main question. Okay, so if you wanted to ask, okay, I wrote some history on the board. If you want to ask analogs of all the questions that we first asked when we learned about Jacobians. Maybe the first question, if you want to directly copy what you had here, you might maybe want to ask how large is the subgroup of like homologically trivial one cycles, more rationally trivial one cycle. I want to write on the board and just say that this is a really, really hard question. Like even over things like the complex numbers, it's very hard in general to come up with elements in the subgroup, leave alone show that they're not in a smaller subgroup. This is a very large question, a very difficult question. I mean, a lot of papers, like even the early 90s, are about constructing examples of varieties where we can show this group is large or small or something. Like this group can be like infinitely generated. There are examples of boson, several others. But over like small fields, like number fields, so those are all examples constructed over large fields, but over a field like a small field, like a number field, the expectation is that this group is small. This is like the subject of valence and block conjectures. This is conjectured to be finitely generated over a small field, and like its rank is supposed to be controlled by the order of vanishing of an L function, so on and so forth. But like I'm not going to talk about this. This is a hard question. Instead, I made you an example of a particular element in this group. I'm instead going to ask, just focus in on this one element. It's like giving ourselves 1 point in the Jacobian. I just want to ask how deep in this filtration I made here, how deep in this filtration, that's the Chirisa cycle level. So studying the whole group, we focus on one element. Okay, so far so good. Yeah, please do continue to ask questions, even if they're about base points. So here are some answers. So one thing that you get right away, and one thing I get by cleverly taking the difference of these two copies of the curve, is that x minus is actually homologically trivial. Right, so and this is actually one of the naturally occurring examples of homologically trivial cycles. So why is this? Both x and its image under -1 go to the same class in homology. If you look at what pulling back by -1 does on homology, like it does not nothing. -1 upper star acts trivially on H2G minus 2. Like you want its wedge 2G minus 2 of H1 on the Tate module, -1 acts by multiplying by -1 on H2G minus 2, it does nothing. Right. So the cycle is already one level in this here, and the question is, does it go any deeper? Okay. And of course the answer depends on which curve you have, and it also depends on the base point. Right? In full generality, depends on the input. And if you have to start playing around with examples, I don't know about you, but I mean, my favorite class of curves is like the hyperelliptic curves. I can write down nice equations for them. And but for hyperelliptic curves, turns out, and if you choose a y-stress point, turns out that the cycle is actually not that interesting. X minus is actually 0 in this group, even before like.
You mean P by B?
Oh, yes. Yes. Take in the other direction. Right. So the cycle is actually 0 on the nose because this picture is misleading. X and X minus are the same. The hyperelliptic involution induces -1 on the Jacobian. So you have this nice commuting square, and then X minus is actually 0. All right. They're like, okay, the first class of curves I can think of, like this is not terribly interesting. You have to go on, keep looking. I usually like asking people, like, if they had to choose one curve to ask this question about, what do they want to know? If they have a favorite curve, they want to understand the Chereso cycle of. Usually different people, very different answers. Okay. If I allowed you to ask this question one more time, like, tell me the Chereso cycle of blank, which curve would you choose?
Quartic.
Quartic, yes, I will say something about the quartic. But if I only allowed you to ask this question once, maybe you want to know what happens to the generic curve. But yeah, I will also say something about the quartic. The Chereso, his 1983 PhD thesis was about very general curve of genus at least 3. You can see why he said genus at least 3, genus 2, every curve at least hyperelliptic. And he showed that the Chereso cycle does not go any deeper in this filtration. It's not in V1 J. And actually, he proved something stronger. He showed that no multiple of it stands in this, goes any deeper in this filtration. So for that, and very general, because his tool, the main thing that he used for thinking about this question was he used tools from Hodge's theory, and like he degenerated this curve to the boundary of MG. He looked at a curve degenerating to an elliptic curve on to a curve G minus 1, and use tools from Hodge's theory. Like I wrote down those maps at the beginning just to say, like, one of the tools we have for understanding points on Jacobians is like integration, like, mapping. And he was able to use degeneration, complex Hodge theoretic tools to show that the Teresa cycle does not actually go any deeper in this filtration. And Alex and Wang and Lee have are this ongoing work to try and build a periodic Hodge theoretic analog. And I think Alex should correct me if I say something wrong. This probably gives like stronger kind of non-vanishing results for this cycle. Like,
Yeah,
yeah,
different.
different. It plays like, yeah, the complex results is like a very general curve. It's not going to have, it's going to have a Teresa cycle that's not algebraically trivial and like, yeah, the Hodge theoretic analog of this that gives a non-vanishing result of a different flavor. So I said, okay, for the very general curve, this is what happens, but maybe this is not satisfying. Like Kiran, maybe you want a curve that you can actually write down, right? So the first example of a curve, an actual equation, this is quartic. So Bruno Harris studied the Fermat quartic. So there's an equation like the fourth. And he showed this time actually by computing some integrals, he showed that the Teresa cycle of the Fermat quartic is not algebraically. Okay, and what he did was the analog of what you do for Jacobians. Like the Fermat quartic is very, very special. We understand its period lattice, like it's in the Gaussian integer. So what he did was actually compute some kind of period integral and showed that it was irrational. Approximated it enough, it's like a nice 2-page paper where he computes an integral. There's bare hands, it's like 1.7 something, and he enough precision, and he was able to show it's not an integer, so the original thing not up at 0. I put these two results side by side to like, okay, someone will ask a question like, Teresa showed that the generic curve, no multiple of it is algebraically trivial either. So that maybe that's the result I hope to prove. And Locke actually showed this for the Fermat quartic. Times no multiple of the Teresa cycle of the Fermat quartic lands in the subgroup of algebraically trivial cycles. And what he did is Bruno Harris used like integration like over the complex numbers. Locke's tool was to look at was to map logically trivial into something like the Selmer group. So he used the Aladic Jacobi map. So he again, like using the very special structure of the Fermat quartic, he was able to show that the image under the Aladic Jacobi map is infinite order. Okay? So and since then, bootstrapping techniques introduced here, complex integration and the Aladic Jacobi map, like we know we can prove similar results for various low degree Fermat curves and their quotients. We can mention a whole lots of names. I apologize for that one. Yeah, drop in his thesis, in his 3 curves divided in a triple product of elliptic curves, the results of Kimura, Tadakuru, Tsubo, so on and so forth, like or modification of these techniques. this was again like in the early 90s. More recently, was our inspiration for this work was the result of Eskandari and Murthy from 2021. They were the first ones to study a whole infinite family of curves. So they studied Fermat curves, bigger than 7. And they were able to show that n times the Cheresis cycle of the Fermat quartic. I shouldn't have called this P. There's a reason I had n in my notes. I'm changing this to M. It's not rationally trivial. And they also like that proof also makes crucial use of the fact that these are like special curves. They used they had an interesting mix of like number theoretic and geometric inputs. Somehow they were able to reduce this question about one cycles and Jacobians back to like questions about points and curves. So like somebody else did. Right. So their main idea was to again exploit the symmetries of these curves. So they were able to perform. I'm just summarizing this, but like so the question about cycles becomes like much harder. When you're talking about cycles of codimension bigger than 1, it's much like quite difficult to get your hands on, but they were able to like somehow use the fact that this curve has automorphism and use that automorphism to like map this complicated cycle and send it back to a point in the Jacobian. And luckily, we know quite a lot about the arithmetic of Fermat Jacobians. Like for instance, we know that that J of Q is like there's this P bigger than 7. We know that this is infinite. We know that torsion is supported on the cusps and so on and so forth. So they were able to explicitly show that this will match to a point that is probably of like infinite order, like using results of Lewis and Ehrlich's. Okay, so this was again like 2021, and just in the last few years, there have been like other examples that kind of inspired by this kind of technique to use study special curves with symmetries and exploit the symmetries to say something about the Cheresis cycle. So Jeff Lauter, Ari Schnittman have a paper from this year where they study genus 3 Picard curves. So this is genus 3 curves with an automorphism, and they're also able to produce from the Cheresis cycle a point on an explicit elliptic surface, and they show the Cheresis cycle's infinite order exactly when a point on an elliptic curve, associated elliptic curve, is infinite order. They use you need all the machinery of Chow motifs to make this work, but like at the end of the day, it's like use the symmetries to do some kind of dimension reduction and like yes.
Since I asked about the Klein quartic, maybe I should ask if I specialize this to the Klein quartic. Do you know whether you get order or not?
Klein quartic has infinite order. Actually, these guys like or maybe I shouldn't just pick out because they actually study all of M3 like stratified by the automorphism group, and I can tell you exactly what happens in each strata. So there's a very nice table in that paper. Yeah, you can see pretty well. Another answer I could have gone for favorite curve is like modular curves. So these have also recently been studied by Kerr, Songling Shu, Songhan Yang, again a paper from earlier this year, where they're able to show that most modular curves, apart from some finitely many exceptions, have infinite order Terrace cycle. And again, they use modular curves come with all these Hacker correspondences. So they're able to again use some dimension reduction using Clashes cycles and modular curves. So this is this is like most of the examples we have in our pocket. We might ask, what happens if I close my eyes and pick a curve at random? All right, like all of these arguments really made crucial use of another eraser. All of these results I mentioned so far, all of these apply to curves with automorphisms. But an equation that you're likely to write down at random, likely to be a curve which has no automorphisms. So what can you say? This phrase is vaguely, but it say the precise result in this. What can you say about the Teresa cycle of a random curve? It's unlikely to have any special structure. Okay. You have to guess what's going to happen. Maybe like going off Teresa's result for the generic curve, maybe you would guess that that an equation you're going to write down at random, you will have something of infinite order. This might be your guess. But can you actually like certify that this guess is actually correct? So that's the flavor-based main theorem. This is the algorithm that's joined. Lindbergh and Adam Logan, which is based on discussions. So the input for our algorithm is like the equation for a curve or a number field. So we've got a nice smooth projective geometrically entangled curve with a number field. And the output is either a certificate. Our algorithm will run, either produce a certificate that the Teresa cycle has infinite order, or it won't, or keep going, or it won't terminate. You cut it off. And in this example, we ran our algorithm on where did this go? For example, when we ran this, the database of like genus 3 curves with like small coefficients, there are 250,000 approximately genus 3 height 1 smooth clean cortex. This means pick your favorite equation with coefficient 0, +1, or -1. So the form. Pick coefficient and -1, 0, 1. In almost every single case, we ran this algorithm on Magma, and the algorithm only failed to produce a certificate in 102 examples. It failed to terminate 102 cases. So in the remaining, i.e., in the remaining, there's 102 examples. These have probably infinite order. Here's the cycle. In this is for infinite order Chirus cycle in the group of logically trivial cycle. Trivial cycle. So that's the chart.
So
Yes.
just the issue of the base, choice of the base point. So you just,
We pick the
Right.
canonical base point. So if we know that for most base points, the cycle is of like infinite order. So this question is only interesting if you choose a base point whose 2g minus 2 is multiple as the canonical point. So we prove it from that example. Any other questions, please, guys?
In this output, the CXB modulo something has infinite order.
Yeah, in the Chow group, homologically trivial cycles mod. Trivial cycles.
So what exactly the output? So
Output, it'll tell you, it's a certificate that we know for sure that the Chirus cycle is infinite order. It's a yes or no question, like, is the Chirus cycle infinite order or not? And we're able to say yes.
So it's some theorem that says, when such a certificate exists, then the cycle has infinite order. The certificate feed into that theorem.
and
Exactly.
but it presumes that the algorithm terminates.
Good question. I will have to thank you for one of your theorems at the very end of the talk. The algorithm. Okay, I can spoil how many? Oh, I'm 40 minutes in. I can say, like, in some cases, the algorithm will probably, if you let it run long enough, like in the generic case, the answer it produces exactly coincides with whether Chirus is infinite order or not.
There are some conjecture that terminated.
So I guess we're asking, do we expect it to always be infinite order, or do we know examples where it's not?
Oh, great question. Okay. Hyperellipticals, I told you, have trivial Chirus cycle, and for a very long time.
That's the equivalent, right?
No, it's not. So this was like some of us thought about this at this MRC many years ago. There was a math overflow question by Jordan, said our Chirus cycles, the only examples with torsion are the only curves with torsion Chirus cycle.
Oh, sorry,
No.
I was thinking about trivial, not torsion.
Trivial. Oh, that we still don't know. That's interesting.
Okay, that wasn't.
Yeah, all the examples. The algorithm that I show you can produce low bounds on the
We don't know
order.
that trivial implies hyperelliptic.
Yeah, we don't know that yet. There are lots of open questions.
Sorry.
From this definition. Sorry, what did you just say, Mignon?
Is there some conjecture that implies that?
I'll tell you what the algorithm is and like our algorithm will not work for certain special curves like the Fermat curve, but like you can like modify it and ask for something else work. Yeah, it's kind of.
So in number field, there's this conjecture that the order of vanishing of the L function, some L function at some point, is the rank of the Chow group. So if the L function doesn't vanish, you expect.
Yeah. So one reason for I said this on the board, maybe worth repeating. One reason for maybe studying this specific cycle is that, and if you're trying to like gather historically, the Chirus cycle played an important role in the formulation of these valence and Bloch conjectures. So what Bloch did was like he was able to provably show. I forgot. Thank you for the question. I forgot to say this when I was writing. Bloch showed that the Chirus cycle has infinite order. He was also able to verify that the corresponding L function had order of vanishing at least one, and he was like, okay, maybe this is not an accident. And he didn't call it a conjecture, he called it a recurring fantasy, and then he has a son of a recurring fantasy. Yeah, these, and like Buehler shown in top actually gathered like by studying the Chirus cycle of genus 3 curves, but special genus 3 curves embedded in a triple product of elliptic curves, they were able to numerically, again, using techniques very similar to what I'm about to present, like to verify the Chirus cycle as infinite order. And those examples, they were also able to numerically show that the L function vanished. And like, at least things seem consistent, but like so far, like we have, yeah, you can use this to like gather evidence for this conjecture, but it's difficult to say in general. Thank you for the great questions. Questions? Maybe I should pause. Okay. I can tell you about algorithm. That was I. Oh, I actually had some remarks to make about this conjecture, about this before presenting the theorem. So all the, interestingly, like, and maybe it's good for our algorithm, all the 102 exceptions that we found, they all turned out to be special curves. They were curves with an extra automorphism group, and they included the known torsion examples, which is good, as they should. Or, oops. Under two exceptions, our algorithm couldn't decide what is happening. These were curves, special curves. We had curves with like these square, at least in their automorphism group, and they include known torsion examples. This is an example. Like Beauville, Jackson, like so there's a very nice criterion that applies in some cases where you can you check the Charissa cycle as torsion, and that involves studying how the automorphism group acts on the homology. And so there are some known torsion examples. Our main tool, I'm going to present the algorithm, but our main tool is to use this Eladic Abel-Jacobi map, the same one that Bloch used. You might ask, in Youngstein, what can happen if we study the p-adic Abel-Jacobi map? So we have, I'm going back with unknown Besser. No, I need help. I think there's also the Jen and Krishnan to explicitly compute the p-adic Abel-Jacobi image of the Charissa cycle in terms of p-adic iterated integrals. This thing, this algorithm, like, okay, well, be able to tell you the cycle, I mean, we'll be able to give certificates for non-triviality even in the Griffiths group. It's a recipe for taking a curve and producing a functional on that takes us input to three Durand cohomology classes and like outputs a number, and we can prove that the number is non-zero, like by computing it to sufficient precision, we can actually certify non-triviality in the Griffiths group. Unlike the complex Abel-Jacobi map, the p-adic Abel-Jacobi map lands in like a vector space. So like this has the advantage of being able to test if something is non-zero. That's easier. So, all right, I'll be ready to tell you what the algorithm does.
So in two, are you really verifying the non-triviality of the mixed type structure on this truncation of pi1? I'm just trying to figure out how you do this with iterated integrals.
So Amnon has this paper, he calls it a generalization of Coleman's integration theory, but he's able to produce, maybe secretly behind the scenes, there is some Hodge theory going on, but like he's able to take a homologically trivial cycle on the Jacobian and produce from it like a functional on H3
Mhm.
of X, and like if something is algebraically trivial, it will vanish. It will vanish on 3, like it will vanish on triples of holomorphic forms. And yeah, there's a description of this image using Coleman integration.
The next is J, I guess.
Oh yeah, sorry.
Okay, and I'm not saying, is there some height pairing also that is implicitly? Or?
I know that I haven't seen any periodic heights in that paper. This is a symptomic. I'm saying words that I don't fully understand. He says he's describing the symptomic Abel-Jacobi image, and he embeds that in some, and inside something computable. He calls it finite polynomial cohomology, where you use usual things that show up in Coleman integration, like parts, those kind of things show up. Okay, so all right. Okay, a lot of interest in this. We're going to talk about this. I tell you about this Elatic result. So the main thing we use, again, like I said before, 5 minutes, like the main tool is, okay, cycles are hard, cycle classes are easier, right? So we, instead of studying the Chiriso cycle directly, we use blocks like refined cycle class map. The stakes, homologically trivial cycles. We don't decide, take what I'll you choose. You can move over. I map it to its homology class, like mapping upon the Jacobian family group. So if there is a cycle, maps to the Chiriso class. And what we actually show is that the Chiriso class has infinite order. You get down. X has infinite order. We get to play games with Galois homology. So we have a there's a two steps to this approach. So the first step is to bound, compute an upper bound on the torsion order. So so in the specific cycle or its class is harder. Let's just try to understand all torsion in this Galois homology group, right? So you can play games with like the Kummer sequence and so on. So torsion. Depending on, maybe people can ask me questions. The idea is to play around Kummer sequence, and you get. I can tell you what this upper bound is. There's an actual computable integer that you can just compute from the L polynomial of the curve by reducing both primes. And you play off this upper bound with the lower bound. Oh, there's the eraser. I was wondering where it disappeared. Choose. Second step is to choose an auxiliary good prime. And compute a lower bound. Answer P. Someone asked me about this. One formula for this on the order of this class, and the algorithm just tests if these upper bound and lower bound are compatible. So you compute this integer n, and answer P for all primes up to some chosen bound. And if you find even one, is P such that n sub P does not divide n. Then the lower bound tells you the order is divisible by something that prevents it from being in the torsion subgroup. If n sub P does not divide n, then you output that the Charissa class has infinite order. And this the main idea for this n sub P actually is kind of inspired by what happens in like Cheverty-Kim. Like there's a way of like thinking about the image of this. There is a cycle in terms of extensions of fundamental groups, and we know, okay, just modulo the third term of the lower central series. Okay, so that's a pretty large extension, but like when you have correspondences, you can simplify that extension and study a smaller bit. If you write down a random curve, like, okay, in general, it's not going to have any correspondences, but it acquires correspondences when you reduce mod P. You have a God-given correspondence. Here's the Frobenius. I write down a formula for the sense of time. But you can use the Frobenius correspondence to produce an explicit lower bound. And yeah, the algorithm is just testing if n sub P does not divide n. And to answer Dick's question from earlier, you can ask if, okay, I chose to run this algorithm and computed these n sub P's for P up to some chosen bound. Well, I mean, if I, instead of cutting off the algorithm, if I let it run for longer, will I eventually always produce a certificate that the Charissa cycle has infinite order? So there's some kind of and we can show that that's indeed the case, at least when the Galva action on the homology is maximal, is actually finite index in GSP2G. If the Galva action on H1 is maximal and the Charissa cycle is infinite order, then these n sub P's is unbounded. P varies. So if you wait long enough, you will eventually find an n sub P that's too big. Okay. I have 2 minutes. Maybe I
Maximum
can
means the Zariski closure is GSP or something.
Yeah. So if this uses your result, crucially uses your result with Matsumoto, and says that under these hypotheses, the Galva action on pi1 is large. And we can arrange for these n sub P's. Okay, let me tell you what n and n sub P are. You can arrange for these n sub P's to get bigger and bigger. And for like Mignon's complementary question, for like the Fermat curve, it turns out the n sub P is always bounded by 4. But we know the Charissa cycle has infinite order. This won't work. So what are n and n sub P? So for n, right, we basically, I mean, the Kumar sequence, or like any module, we know where torsion in H1 of a Galva module comes from. Like, if you want to understand and torsion, this comes from invariance in n mod n, right? So basically, so the relevant Galva module here is like the wedge cubed of H naught. So there is n torsion, and n has to divide this the land, which is determinant minus identity acting on wedge cubed of H1. So this is something you can compute this if you know the L polynomial. Just take products of triples of eigenvalues of Frobenius, and this is guaranteed to be a non-zero integer from like weight. We know none of the eigenvalues are 1, and the fun part, the second part, what these n sub P's are. I said the main idea is that curves acquire, even if the original curve over a number field has no symmetries. When you reduce mod P, you get the Frobenius. So this n sub P is the order. Actually, again, there's some dimension reduction argument. You produce a point on the Jacobian of the curve, mod P. It's n sub P is the order of the following canonical point. on Jacobian of the reduction model. You can ask, okay, what point can I write down on the Jacobian? So you can look at all the points that lie on the curve. Add them all up. Okay, okay, this is not a degree zero divisor, but I know another canonical divisor of the curve, like namely the canonical, and I can take a weighted sum of these two to produce something. So this is the point that lives on the Jacobian. Like so, take the order of this point, and there's something magma can compute. Morally, what's like happening behind the scenes, like whenever you have an additional correspondence, like, I mean, I stated everything in terms of the Cherry's cycle, but there's a very closely related cycle, the modified diagonal cycle, and like you can intersect the modified diagonal with the graph of some correspondence, and what you end up picking up is the fixed points for that correspondence. You know, I use the Frobenius, so I'm getting something like that at P points of the Jacobian. So this is ends up P, like very natural looking point in the Jacobian of any guess. Somehow its order is related to the order of the Cherry cycle. I stop here. Thank you very much.